Okay, now let's talk more about conditional probability. This is the probability of one event occurring given that another event has occurred. So the probability of event A occurring given that B has already occurred is equal to this. The probability of the intersection of the two events divided by the probability of B. The probability that B occurs given that A has occurred is equal to the probability of the intersection of A and B divided by the probability of A. All right, let's put some more real-world perspective on this. Imagine 70% of a nation's population is white, 40% of the population smokes, and 20% are white and smoke. What is the probability that a person smokes given they are white? Let's shift over to paper mode for a moment. Let's rewrite this in terms of our example. So we want to know the probability that a person smokes given that they are white. So I'm going to put up here the probability that the person smokes given that they are white. And that will equal the probability of the intersection of smoking and being white divided by the probability of being white. Okay. And we can plug in the numbers here. What is the probability of the intersection? Well, smoking and being white, it says here that 20% are white and smoke. So we would put 20% here, or 0.20 in our numerator. And then the probability of someone being white, it says 70% of the nation is white. So we put 0.70. Well, 0.2 over 0.7 is about 0.29. From this, we can actually develop what's called the multiplication rule. That is, we can derive the probability of the intersection of events A and B if we know the probability of A given B and the probability of B. This is just a reconfiguration of this formula here, right? Moving the denominator, the probability of B, to the left-hand side of the equation gives us this and solves for the intersection. Just like this one here is a reconfiguration of this. By moving the probability of A to the left hand of this equation, we get this one. And from there, we could solve a intersection problem. It says here, what is the probability of getting a red ace? Okay. Well, let's use our formula. We'll rewrite it to fit the example better. What is the probability of getting a red intersecting an ace? It's going to be equal to the probability of getting a red given that you have an ace times the probability of an ace. Okay? Now, if you plug in numbers, you know that the probability of a red given an ace is 50%. So that's 0.5 or 1/2. Okay? And the probability of an ace is going to be 4 out of 52, or 1/13. So we end up with essentially 1 over 26. Okay. What is the probability of a red ace? Well, there's 1 red ace out of 26, 2 out of 52. So it makes sense. Okay. Next, let's talk about independent events. Two events are statistically independent if the probability of A given B is equal to the probability of A, or the probability of B given A is equal to the probability of B. There is a common sense element to this because let's say that we know the hot weather outside has nothing to do with winning the lottery. Therefore, we know that hot weather and lottery winning is statistically independent. If we try to plug in these scenarios, we get the following. The probability of winning the lottery, given that it's hot out, is the same as the probability of winning the lottery. Okay? We can also evaluate statistical independence with this formula. This says the probability of A intersecting B is equal to the probability of A times the probability of B. If this statement is true, if these do in fact equal each other, we say the events are statistically independent. If these don't equal each other, we cannot say they're statistically independent. For this one, let's practice. It says 30% of a nation's population is obese, 15% of the population is in poverty, and 5% are obese and in poverty. What is the probability that a person is obese given they're in poverty? And are these events statistically independent? Let's plug in some numbers. So the probability of an intersection we can rewrite as probability of being obese and in poverty, obese intersecting poverty, is equal to, it says 5%. Okay. So we know that represents the probability of an intersection. Then we want to see if that's the same as the probability of this times this. So the probability of being obese times the probability of being in poverty. And for that, we know 30% is obese, so we put 30%, and we would multiply that by poverty. It says 15% are in poverty, so 15%, and that gives us 30% times 15% is 4.5%. So the probability of an intersection of obesity and poverty is 5%, but the probability of a multiple of those is 4.5%. They do not equal, right? There is not an equality between these, which means they are not statistically independent. Okay? Another way of putting it is there is a relationship between obesity and poverty, which, even though this data is hypothetical, there is in fact evidence to support a statistical relationship between obesity and poverty in the U.S. population. Right. These formulas carry on for more than just two events. I mean, here we're looking at A and B, and here we're looking at obesity and poverty, but you could have dozens or hundreds of events, and it's the same idea. You take the probability of the intersection of all those events and see if that does equal the multiple of the individual probabilities for each event. All right, that's it for this video. If you have questions, let me know. Thanks.